Okay, so that's f of x. Let's do g of x. So somebody give me some points on g of x.
0.
0? 0 what? What now?
0, 0, 0, 0, 1. Right? It's the same.
You're saying 0 a bunch.
It's the same graph.
No, it's negative 1 and 0 would be.
Thank you. Negative 1 and 0.
Oh, okay.
That's 1 point.
Negative 2, 10, 0 and 6, 1 and 8, and 2 and 6.
There we go. It's the same thing. Should we just pretend that I can draw? Okay, and then h of x. What about h of x? Nick, what do you think?
It's the same exact stuff for
It-
all the points.
It is, in fact, the same as well. So what we have here is the 3 different forms of a quadratic function, and you can see that we can express the same quadratic function in these 3 different ways. So let's grab some information from the graph, and then we'll see how the different forms help us with all these different components of the graph. So from the graph, what's the vertex of this function? So remember, the vertex is just the point where the parabola like turns around.
1 and 8.
Uh-huh. So 1, 8.
Is that like a point?
What's the stretch factor? So remember when we did transformations, right? Like the point 1 unit to the right of the vertex? In x squared, the point 1 unit to the right of the vertex has a vertical distance of 1 unit from the vertex as well. So what's our vertical distance here from the vertex to the point 1 unit to the right of it? 2, yeah. So this distance right here is 2, which means we have a stretch factor of 2. And if you wrote -2, that's totally fine. I mean, technically speaking, the negative isn't part of the stretch, it's the flip, but it's totally acceptable to write either one. It's maybe even a little more intuitive to think of it as -2 because that incorporates the flip as well, but either one's fine. So does this function have a minimum or a maximum? Yeah, it has a maximum, right? Its vertex is the top rather than the bottom. So every parabola either has a minimum or a maximum. And what are my x-intercepts?
-1, 0, 3, 0.
Good. And my y-intercept?
0, 6.
Mm-hmm. And then where's my function increasing? So if we're going from left to right, where are we walking uphill?
From negative 2, 10. From negative 2, negative 10 to
So give me x values.
just x down.
Mm-hmm.
So from negative 2 to positive 1.
So does the graph stop at the point -2, 10?
Oh, it's negative.
Yeah, good. So negative infinity to 1. And then it turns around and goes down, right? So, sorry, my watermark is in the way here. But so on the other side of the vertex, it's decreasing. So parabolas are really nice because they're symmetric, right? So like we call this line right here the axis of symmetry. It's just the vertical line through the vertex. It means you could fold along that line and everything would match up on both sides. So it's always either increasing to the vertex and then decreasing, or it's decreasing to the vertex and then increasing. It can't turn around more than once. So quadratics are always parabolas, so you're just going to have like one interval for each of these. And like when you're doing these, if you don't have the graph, you can like ask yourself if it opens up or down and just kind of like give yourself a little tiny sketch and be like, oh, it's decreasing on the first half and increasing on the second half. So if we look at the things that we just found, like let's start with the vertex 1, 8. Look back up at these functions. Do we see 1, 8 anywhere in these functions? In any of the forms? Like, could I have figured out that the vertex was 1, 8 without graphing from any of these? Think about what we did on Tuesday with transformation.
Could you use the first one?
Yeah, so like remember that x squared has a vertex at 0, 0, right? And this first function says shift left 1, I'm sorry, right 1. And up 8. So if you have the vertex of x squared, which is at 0, 0, and you shift it right 1 and up 8, you get to the point 1, 8, right? So 0, 0, those shifts make the vertex into 1, 8. So we can get the vertex straight from that form because of the transformations that we talked about on Tuesday. Yes?
What is -1?
Right, remember that the shifts go in the horizontal direction, go the opposite way you would imagine them. So if it's a -1, you're shifting right, which would get you to +1.
But then it's +8 and you're still going up 8.
Because that's vertical. So horizontal transformations go the opposite direction, you would imagine. Vertical transformations go the same direction, you would imagine. Right? Remember on Tuesday when we did all those transformations, we saw that, right? And the reason for that is that, like, if you kind of have to think of it as, like, if you wanted to get to the point 0, 0, so in x squared, you square 0 to get an output of 0, right? So what x value would I have to put in here so that I'm squaring 0? So what would x have to be in order for the thing that I'm squaring to be 0? Well, 0 minus 1 isn't 0, right? The thing I'm squaring is x minus 1. Yeah, x would have to be +1 in order for x minus 1 to be 0, right? So to get to this same y value, my x value has to be 1 more so that the number I'm squaring is 0. You're sort of thinking of it backwards, right? To get to the y value I want, I have to solve for an x value, which means we do opposite operations to get it, right? Whereas to get a y value, we're just plugging numbers in and doing calculations. So in the x direction, everything is always the opposite because we're thinking about, like, how to get back to the y value on the original function rather than, like, building up the new function. So that's why, we haven't gotten there yet, but we'll see it in a minute. 8, like, we always think of that number in the parentheses as the opposite of the direction we're going. So what about the stretch factor? Do you guys see that anywhere? So I purposely made every single number different in all of these so that you could only see each number once. Or in one place, I guess. What do you think, Braden?
Well, I see that they all have a -2.
Right, and so on Tuesday, where did we put the stretch factor when we were stretching? Yeah, right? So we subtracted or added something before squaring. That shifted right or left. Then we squared, possibly added something or subtracted something to shift up or down, and then multiplied, right? And that's how we stretched, was to multiply. So this number right here gives us our stretch. I mean, it also gives us our flip, but gives us our stretch factor. And what's cool is that it's the same no matter what form we're in, right? So you can even like with the vertex, you have to be in the form of the first equation in order to figure out what the vertex is from the equation. But you can figure out the stretch factor of a quadratic function from any one of the forms because it's always the same. What about the x-intercepts? Do you guys see the x-intercepts anywhere?
Third equation.
Yeah, that one's in factored form, right? So to find x-intercepts, if we set that function equal to 0, we'd have x minus 3 is 0. That gives us our 3. And x plus 1 is 0. That gives us our negative 1, right? So just built into that equation is our x-intercepts. What about the y-intercept? Yeah, in the second one. So remember that when we did lines, we had like mx plus b, and b gave us the y-coordinate of our y-intercept. Well, that's actually true of every single polynomial function. The constant term always gives you the y-coordinate of your y-intercept. So even if I had something like x to the 20th minus 51 x to the 12th plus blah, 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 a bunch of stuff with x's in it, plus 3, like my y-intercept would be 0, 3. So it's just the term that doesn't have any x's in it, because all the terms that have x's, when you put 0 in, they just go away. So it's always the constant term, as long as it's in that form where it's all simplified and multiplied out. So let's summarize these 3 different forms of quadratic functions. So all of them are useful for different things, right? And we use them in different ways. So the general form of a quadratic function is kind of what we see the most, because it's kind of how these are usually presented, because it's fully simplified. So if we're given a function, oops, we are often given it in this form. If we're trying to build a function, it's not super duper useful. Oh, Eli, come get. Oh, I'm sorry. There you go. If you're trying to make a function, this one's not super handy, because the only thing it really for sure is the y-intercept, and that's just like 1 point. And there's an A, a B, and a C in it, so you can't really figure out A and B just knowing what C is, right? So writing functions, general form isn't super helpful, but we often see them when we're given the function in that form. So factored form, well, we get a bit more from factored form, right? This one is fully factored. And we know that if we set it equal to 0, that we get x minus m equals 0, x minus n equals 0, so x equals m, and x equals n. So I can get my y-intercepts directly from that form. And that's a bit more useful when we're writing functions, because if I know my x-intercepts, that automatically gives me my factors, which we'll do quite a bit. We're going to focus on factored form on Monday. So we'll do a bunch of that. The last one is standard form of a quadratic function. The unfortunate thing about standard form is that it's not, like, usually when, like, if you're given a quadratic function, it's usually not handed to you in standard form. It's super useful because we saw, like, on Tuesday, it tells us exactly how x squared has been transformed to get it, right? This is what I gave you at the very end of the day on Tuesday. I said all of them were in this form. This is our stretch. This is our horizontal shift. This is our vertical shift, right? So you can sort of get the entire function from that. But in particular, so this is not factored or simplified. It's like a hybrid of the two. But it does give us our vertex, which is really handy, right? So if I took the vertex of x squared, which is 0, 0, h shifts it right h units, and then adding k shifts it up k units. So my vertex is hk. And then for all of them, we already saw that like A is the same. If A is positive, which way do you think it opens? Up, right? If like x squared opens up, right, and has a positive 1 as its coefficient. So if A is positive, it opens up like this. If A is negative, it opens down like this. So opens up. And the most interesting thing we get from the fact that it opens up is that it has a minimum. Right? It has a local minimum, but it has no local maximum. And then if it opens down, it has a maximum. But no local no local minimum. So this is important because remember the problems we did the other day with the graphs where we were optimizing, so we were finding like the minimum area or the maximum area. If we have a function that opens up and I say what's the maximum, like the only way to get that in an application problems is to use like the physical restraints of the problem, right? That like time can't be negative or like area can't be negative because there's no local maximum to find there, right? If it opens up, we can't be like, oh, what's the maximum revenue or whatever if it's the revenue function and it opens up. So it's important when we do these optimization problems to know which way it opens, because if it's not your local maximum or minimum that's going to do what you want, you have to like look at the edges, right? Based on like the physical parameters of the problem, which is usually just that nothing can be negative, right? So from here, we're going to just start focusing on specific forms. So today we're going to focus on the standard form of quadratics, and then on Monday we'll work with the factored form a bunch more. So the first thing I want to do here is find the vertex, and we should be able to do that directly from the function. What do you guys think the vertex is?
1, 3.
Mm-hmm. So 1, 3, and I get that because this is a shift left. I keep on doing that. Ass backwards today. Right 1 and up 3. Right, before squaring, I subtracted 1. That gets me a horizontal transformation. And after squaring, I added 3. That gets me a vertical one. So then how do I find x-intercepts of a function? What now?
X plus 1 and x plus 1. Well, or x equals 1 and x equals 1. Those would be
So remember, this isn't in factored form, right? That would be true if the 3 wasn't there. But it's not a product. So, like, x minus 1 times x minus 1 isn't equal to 3.
Well, I was saying you set them equal to 0. So
Right,
x
I know,
minus
but,
1
like,
squared, yeah.
so if you had x minus 1 times x minus 1 equals 0, then that would work. But this isn't factored, right, because of that addition right there. And so, like, if x minus 1 was equal to 0, the output of this function would be 3. Because we have to add the 3 after multiplying the zeros. What else? How do we find x-intercepts? Every single time we find an x-intercept. I'm just going to wait because like we've done this for the past 3 days and I know you guys know it. The first thing you do to find an x-intercept is what? Yes, you set your function equal to 0, right? That's what an x-intercept is. It's a point with a y value of 0. So you have to make your output 0. So negative 2 times x minus 1 squared plus 3 equals 0, right? We're solving f of x equals 0, which is how you find the x-intercept of any function, like quadratics, linears, rationals, every single function in the whole wide world. To find the x-intercept, you set your function equal to 0, and you solve. So how many times do you guys see the x here? Once. So our three choices for solving quadratics are to use the square root property, factoring, or the quadratic formula. If we see the x value once, which one of those do we use? Well, let's narrow it down. Do you guys know what a, b, and c are based off this form? No, we don't have ax squared plus bx plus c, right? So using the quadratic formula isn't going to work very well. And then, is it factored?
No.
It's not factored, so solving by factoring isn't going to work too well. So there's only one other choice. What is it? Yeah, to use the square root property, right? We have something squared right here. So if we get that alone, we can take the square root of both sides. So we have negative 2 times x minus 1 squared equals negative 3. Divide both sides by negative 2. And then take the square root of both sides. Remember, every positive number has 2 square roots. So we get x minus 1 equals plus or minus the square root of 3/2. So x equals 1 plus or minus the square root of 3/2. You don't have to do any simplifying of that radical, like just leave it as it is. It's kind of ugly, but it's fine. So my x-intercepts are 1 plus the square root of 3/2, 0, and 1 minus the square root of 3/2, 0. In particular, if you look at the three forms of quadratic functions, these correspond to the three methods we learned for solving a quadratic equation, right? If we have the standard form set equal to 0, or sorry, I'll start at the top. If we have the general form set equal to 0, then we can use the quadratic formula because we have an a, b, and c. If we have the factored form set equal to 0, well, then we can solve by factoring, right? Because it's already factored, and just set each factor equal to 0. And then if we have the standard form equal to 0, we have our x only appears once, which means we can isolate that x, that's something squared. In this case, x minus h squared, and then take the square root of both sides. So we learn these three different ways to solve quadratic equations, and those three methods correlate exactly with the three different forms of the equation, which is really useful because it means that when I'm given something like this, I don't have to multiply x minus 1 by x minus 1 and like reconfigure the whole thing just to solve the equation, right? I already have a method for solving an equation that looks like that built into it. So that's another reason, like I was saying yesterday, you don't want to just get stuck with doing it one way. Like, oh, I'm going to use the quadratic formula every single time, because then you just open yourself up to make mistakes getting this in the right form to use the quadratic formula. If you use the one that's most efficient for each one, then you're not going to run into trouble with like multiplying things out and like making mistakes simplified. What about the y-intercept? How do I find the y-intercept of a function? Yeah, you plug 0 in for x, right? So we evaluate f of 0. And again, that is true of every single function. None of, like, the things that we learn about finding intercepts are not specific to any type of function that we're studying. It has nothing to do with whether it's linear, quadratic, or one of the other ones that we're going to do for the rest of the semester. You always evaluate f of 0 to find a y-intercept, and you always solve f of x equals 0 to find x-intercepts. So f of 0 is negative 2 times 0 minus 1 squared plus 3 equals negative 2 times negative 1 squared plus 3. Well, negative 1 squared is just 1, right? So we have negative 2 times 1, which is negative 2, plus 3 gives me positive 1. So my y-intercept is 0, 1. So now I want to sketch a graph, and it kind of sucks because like my x-intercepts are like kind of lame, right? Like I have no idea what values those are. I could plug it into my calculator, and then I'd have to like estimate where they are on the x-axis. But I actually can't, if you know the vertex, you actually only need one other point to graph the entire thing because of symmetry. So if I know, if I know the vertex is, what would we say, 1, 3? And then I know the y-intercept is 0, 1. Well, remember that axis of symmetry goes through the vertex. So if there's a point 1 unit to the left of the vertex with a y value of 1, there is also a point 1 unit to the right of the vertex with a y value of 1. So this has to be a point as well, which I can get without plugging anything in. It's just the fact that when you fold across that axis of symmetry, if you were to fold on that axis of symmetry, it has to be the same on both sides. So parabolas are always symmetric in this way. So if I had a point 5 units to the left of the vertex that had a y value of 7, I would also have a point 5 units to the right of the vertex with a y value of 7. So if you have the vertex and you have any other point, you can just flip that point over, and then you have the whole parabola. So this guy's going to go like this. This guy's going to go like this. And there's our graph. Questions so far? And you don't have to actually draw this axis of symmetry. It's just sometimes nice to like see it so you can think of like folding or flipping. So far, so good? Okay, now we're going to go the other way. So we just use the function to find some characteristics of it. Now we're going to start with characteristics of a function and write an equation for it. So here we're told, so it says find a function f such that the graph is a parabola. So as soon as I see parabola, I know this is a quadratic. These are important things to note because even though like today all we're doing is quadratics, on the final you're going to have to write functions for quadratics, linear functions, exponential functions. Like, so you need to know which words, like which clues tell you like what type of function you're actually writing. Because, I mean, wouldn't it suck if you wrote a linear function for an exponential model, right? Like, so there's always words in there that tell you what type of function it is. In this case, the word parabola tells us that it has to be a degree 2 polynomial. And that's how we know that we're going quadratic rather than linear or something else that we haven't learned yet. And then it tells us that it has a vertex of 4, 1. And so I think back to myself, well, which one of the forms of the quadratic function had to do with the vertex? Which one was it? Yeah, standard form, right? And so as soon as I see that I have a vertex, that tells me that I have to use standard form. And that's important because if you don't pick the right form to use, you're not going to have enough information to write the function, right? If I said factored form, in order to write something in factored form straight from the information given, the information that is given would have to be the x-intercepts, because those are the only ones that actually show up in the function. It's true that all of these can be manipulated to equal each other, but if all we're starting with is a few points, in order to write the function, they have to be the points that we can actually put into that form, right? So standard form is f of x equals a times x minus h squared plus k. And then we're given our vertex, right? So this is my h, and this is my k. So f of x equals a times x minus 4 squared plus 1. So we just did so part A of the last problem, we just did that process backwards, right? Instead of pulling the vertex from the equation, we just put the vertex into the equation. And then now we're just missing one thing. We're missing A, right? We don't know what that stretch factor is. And that's where that second point is going to come into play. I know that when x is 8, f of x is negative 7. So I can replace f of x with negative 7, and I can replace x with 8. So 8 is my output. No, I'm sorry, I did that backwards. Negative 7 is my output when 8 is my input. And in this form, I only have one unknown, right? A is my only unknown, so I'm going to solve for A. So we have negative 7 equals a times 4 squared plus 1, which gives me negative 7 equals 16a plus 1. I strongly, strongly recommend that when you square the 4, you put your 16 in front of a. I see a lot of people do 16 plus 1 because they keep the 16 on the right side of the a, and it's just too tempting to add the two numbers. Like if you write this, it's just so tempting to add 16 and 1 that it's hard to resist. So if you put it in front, then it looks more like what we're used to solving, right? We subtract 1 and then divide by 16. So that gives us negative 8 equals 16a. Divide both sides by 16, and we get negative 1/2 equals a. So my function is f of x equals negative 1/2 times x minus 4 squared plus 1. So once you find your a, you're just going to go back to your general form of the function. I shouldn't say general in that way. Standard form of the function with your a. Does that make sense? And again, the key to all of this is knowing that you have to use standard form because you're given the vertex. If we tried to use factored form or general form here, we'd be kind of in trouble because we have nowhere to put the vertex in those two forms. So I want you guys to try the last one. And so I'm going to write f of x equals a times x minus h squared plus k. And kind of similar, you guys all got this, but kind of similar to how we used that negative b yesterday. You can think of that as sort of the opposite of h. So in our case here, h is a negative 3, so that's going to be a plus h, or a plus 3. So f of x equals a times x plus 3 squared plus k. Nope, plus 6. And then we'll plug that point in, so 9 equals a times 0 plus 3 squared plus 6. That gets us 9a plus 6 over here, which gives us 3 times 9a, so a is 1/3. And so f of x equals 1/3 x plus 3 squared plus 6. And I think that's what I saw on everybody's paper. Awesome. Very good. We have 9 minutes to talk about. I'm trying to throw this in. I've been trying to find some time to throw this in because I'm like grading your exponent homework, and there's like a few things that happen a lot. So like I wanted to talk a little bit about negative exponents. So like if you're simplifying, let's say like 4x to the negative 2 times y to the 5th over like negative 3x to the 7th y to the negative 8th, all raised to like the, I don't know, 5th. Oh, let's make it negative 5th power. So let's just think about what's in the parentheses for a minute. It is true that you can go, like, you could do this. This would be true to write this. But, I mean, in my opinion, that seems really obnoxious to work with. Like, all those little fractions within the big fraction is like just uber overwhelming. Like I would never want to write it that way. It's not that it's inaccurate, it's just that it's a mess, right? Like it's going to take a bunch of simplification for me to get that to a single fraction. So instead, rather than starting with those negative exponents, I'm going to use my quotient rule first and just subtract my exponents. So I'm going to say this is 4, negative 2 minus 7 is negative 9. So x to the negative 9th. And then 5 minus negative 8 is positive 13. So this is y to the 13th. The result of the quotient rule always goes on top. And then if it happens to be negative, we'll deal with that in a minute.
And you should always subtract them?
Yes. So top minus bottom ends up on top.
Because I was thinking you cancel them, so it'd be negative 3 on the bottom or something like that.
So you
Like
can't
the
cancel when there's negative exponents because there's no way to like write out negative 8 factors of y. Right? If that was a positive 8, then yes, I could cancel 5 factors and I'd end up with 3 on the bottom. But when there's a negative exponent, it isn't actually 8 factors of y. So we have to get positive exponents before we can think of it in terms of canceling. So then I'm going to apply that negative 5 exponent to all the factors inside. So this is 4 to the negative 5th, x to the positive 45th. Oh, crap. Why did I do that? 65, negative 65th, over negative 3 to the negative 5th. Y'all put your negative bases in parentheses. Most common mistake with exponent problems is to not put that negative 3 in parentheses. Remember that like negative 4 squared and negative 4 squared are different things. So you need those parentheses in order for the signs to work out the way they should. And so don't just think them, write them. Because sometimes I'll watch you guys do it and like you know it's in parentheses, like in your head it's in parentheses. You're treating it like it's in parentheses. You just don't write them. So just make sure you're putting every negative base in parentheses. And then from here, we'll deal with negative exponents. And so again, like it would be accurate to say that this is 1 over 4 to the 5th times x to the 45th times 1 over y to the 65th over 1 over negative 3 to the 5th. I'm not saying that that's not true. I am saying that that is a really cumbersome way to do it. right? Like that, it's not fun to simplify when you have all those little fractions in there. And so the way I think of it is that a negative exponent just means to take the reciprocal. So the reciprocal of anything on top, it goes on the bottom. The reciprocal of anything on the bottom goes on the top, right? So if you just go through factor by factor, so draw a line, and then say, okay, 4 to the negative fifth, that has a negative exponent, so it has to move down to the bottom to get a positive one. So that's 4 to the fifth down here. X to the 45th has a positive exponent, so it's going to stay where it is. So x to the 45th. Y to the negative 65th has a negative exponent, so it has to move. So y to the positive 65th comes down here. And then now working on the bottom, we have negative 3 to the negative fifth. That's a negative exponent, so that pops it up to the top. So anything with a positive exponent stays put. Anything with a negative moves. So this is negative 3 still in parentheses to the fifth. Right? And then we didn't have to deal with all those little baby fractions and figure out what the heck to do with them. You can just do it factor by factor by factor. And as far as like evaluating these, like on the homework, there was like a 4 to the 12th. Like, just leave it as 4 to the 12th. Unless you, the rule I usually use is if you know what it is without punching it into your calculator, like, sure, why not? So like if you get like 3 squared, you might as well write it as 9, right? But these grow so big that it's like not practical to write them in their expanded form. It's more practical, like 4 to the 5th is a huge number. It's more practical to write it as an exponential expression. So if you don't know what 4 to the 5th is just off the top of your head, just leave it as 4 to the 5th. Because what we really care about here is just manipulating the exponents. We don't really care that much what 4 to the 5th happens to be equal to. Does that make sense? Okay. I think I have a couple more of those homeworks to do before I'll give them back to you on Monday. But I was seeing like the 1 over whatever a bunch of times on the homework, so I just wanted to kind of address it so you guys could see a way to do it without having to deal with all that.